This next problem, number 2, B, I should say, Olympiad, is a classic Olympiad kind of problem where they give you a very complicated looking structure, and then, so this is just complicated looking as it is, then they give you a lot of text, especially compared to the previous question, and you are not allowed to obviously ask any questions. So if there's anything in here that you don't understand, and you can't understand it by looking at this diagram, well, you can't make much progress. So this is a classic Olympiad kind of question, and the only way to get better at these is to, you guessed it, practice. Okay, gotta practice. So let's do 2 things. Let's read the question, let's look at the diagram, and then see if we can simplify. The smaller figure in the diagram has an area of 14 square units. The larger figure on the right is produced by doubling the side lengths of the smaller figure. We know that the smaller figure has 14 square units. Question time. What is the area of the larger figure in square units? All right, well, let's try to interpret some of this. When I first did this one, I was a little bit confused about this photocopy version, but I realized what they were saying is this over here is the smaller figure. Therefore, this is the larger figure. And that made sense to me once I realized that. Okay, the smaller figure is 14 square units. Now you can verify that if you want to, literally by counting them. In order to not get lost, you could probably just draw grid lines, I suppose, like this. And then you could just put a little X in each one that you count. 1, 2, 3, 4, 5, plus 4 is 9. Plus 3 is 12, plus 2 is 14. Okay, verify there's 14 there. Now, let's look at the bigger one. If I were to brute force this, here I am, coming back to that word, brute force this, I could get the right answer for this. Force. The right answer, by the way, is 56. 56. Now, I could count 56 of these squares. I could literally draw a line down here like this. And draw a line here like this, and like this, and then I go like that. But as you might guess, what is the problem with this strategy on this kind of a problem, kind of an Olympiad problem? It takes too much time. So one of the issues with this method is there's too much time involved, and there's also too much error. You could really make a mistake off counting these. Okay, so how do you solve this in an elegant way? Well, let's go back and look at the question. It says the smaller figure is 14, we got that. How did they get from, there's a relationship here, there's a relationship between small and big. How did they get from small to big? Well, they did it by doubling the side lengths of the smaller figure. Okay, well, if you double the side lengths of any figure in mathematics, you increase its area by 4. And this is one of those things that, unless you really have some concrete examples for, you're not going to get your head around this. But I'll try to show you an example here. Let's say I have a square of the side length of 1. Okay, let's say I now double the side lengths. I forgot how to spell the word double for a second. Double the side lengths. I'm going to try to draw this somewhat to scale. Okay, so 1 doubled is 2, and 1 doubled is 2. Okay, now I ask the question of both of these, what is the area? Well, the area of this one is clearly just 1 square unit. Well, what's the area of this one? Well, 2 times 2, which is 4 square units. So even though I have doubled, which in your mind is an operation of times 2, the area hasn't just times 2, it's times 4. Because the doubling has happened to 2 sides. It's a 2-dimensional object we're talking about. Whoa, mind blown. Now you might say, Mr. Black, that's great and all, but whatever. Well, here's why this is so important. This concept here is why you have a smartphone in your pocket. It's why your smartphone is billions of times more powerful than a rocket on, say, the Apollo space program. Hang on 1 second, pause. Okay, I'm back. Is this recording? Oh, it is, good, okay. So what did I mean by that statement about the Apollo program? Well, Well, what goes for growing also goes for shrinking. So let's say that you have a, let's call it a transistor, a fundamental building block of a computer, and let's say it's this same size. If you can just get it to half its original size, okay, you don't have to go crazy, I'm gonna get it 99% smaller, just get it half smaller, then it will take up this much space now. And look, you've actually freed up a lot of room in the original space for your transistor chip. So the computer or the chip you were designing didn't just get twice as fast because you halved it, it got 4 times faster. So this sort of ridiculous trade-off between area of 2D surfaces from doubling side lengths has given us really an inheritance of incredible technology. Anyways, that's a bit of a segue. Back up to the shape here. So I did all that to say, if you are increasing the side length of a shape by 2, you're doubling it. Well, what you're really doing is increasing its area by 4. So another way to say that is that this big shape here is 4 times the size of this small shape. So without even counting these, how could I solve for that? Well, if I go back here and read 14 square units for my shape, so that's a very simple operation. 14 times 4 will give me the area measurement. You can do this a few ways. If you're not comfortable with 14 times 4, you could do 10 times 4, which is 40, and then 4 times 4, which is 16, and then 40 plus 16 is 56, and that's how I got 56. So I know that's kind of a convoluted, long answer for maybe what is a short problem, but I think there's a lot of deeper stuff here that's really exciting to think about, and it's only the tip of the iceberg. Okay, well, hopefully you guys got 56 for this one, and let's go do number 3.